In this video, we're going to discuss angular momentum. Angular momentum is basically just momentum, but in terms of rotation. And so we can find the units of this, which will have the kilograms meters squared from the rotational inertia. And when we have this angular velocity, we know it's radians per second, but a radian is not really a unit that you use. It's more of just saying it's in terms of radians. And so you'll get this unit of, this should be kilograms meters squared per second, which is our same as our momentum unit. Okay? And so we can actually derive this linear momentum equation in kind of a couple different ways. And the first way we'll look at it is using this Newton's second law in rotational form, where we have the torque is equal to the rotational inertia times the angular acceleration. And so we learn that angular acceleration is just the change in the rotation, or the change in the angular velocity over the change in time. And so when we multiply delta t over, you get torque change in time equals rotational inertia times this change in angular velocity. And so this is just the change in angular momentum. And you might be thinking that this kind of looks familiar from when we did impulse with force delta t, and that's because this is what we call angular impulse, which is basically just the impulse, but for angular motion, or like rotational motion. So this is just the angular impulse, which equals the change in angular momentum, just like impulse equaled the change in momentum. And so let's see how we can represent angular momentum in another way from this. And we can start from this equation. So we have, let's say, I equals I omega. And so we know that I just equals mr squared times the omega. And so we also know that the velocity equals r times omega. And so we have an r and an omega right here. So we can take one of those away and just get m times r times v, because there's 2 when you square it. But then we also know that this m times v right here is just linear momentum, mass times velocity, and these are tangential velocities. And so we can pull the linear momentum out and get the angular is the linear momentum times r. And so just like pretty much everything in rotation, the rotational version just equals the linear version times the radius. That's pretty much always what happens. And in this case, this radius would have to be at like 90 degrees. But to account when maybe you're not applying the momentum at a perfect 90 degrees, you can say r times the linear momentum times sine of theta in between. But in most cases, you'll look at where it's perpendicular to the radius, so you won't need the sine of theta term because the radius is already 90 degrees from the momentum. Okay, so let's look at an example using these angular forms of momentum. Okay, so we have a wheel with 50 rotational inertia is rotating, is what that should say, at 8 radians per second. A torque of 7 Newton meters is applied for 3 seconds. What is the angular velocity of the wheel? Okay, and so let's go ahead and list out what we have. We have the angular rotational inertia, so 50 kilograms meters squared. We have it's rotating initially at 8 radians per second. And a torque is applied, 7 Newton meters, for 3 seconds. So we want to know what is the final angular velocity. So that's what we're trying to find, is this final angular velocity. Should say final in there. So we can go ahead and use our equation that we derived as the torque change in time equals the change in linear or angular momentum. So we have our impulse equals momentum, or change in momentum. In this case, it's just the angular form. It's just like we did in momentum unit. And we can go ahead and break out what this momentum is. So we have our final minus initial, and then each one of these equals the I times its angular velocity, so final times the I times the angular initial. And so now we can go ahead and rewrite this equation to get the final angular velocity by itself, like this. Okay, and if we go ahead and rewrite this, we get that the torque times change in time plus the I omega over I. And so now we've rearranged it, we can go ahead and plug in our variables. So we have 3 seconds. And so we were given all of these, so we don't have to do anything special. We can just plug them in. And if we plug all this in, we get 8.42 radians per second. And so that'll be our final answer. And so that's how we can use this change in momentum to find the angular velocity. And so we talked about a few ways now that we can find these different angular velocities of rotating objects using either energy or momentum. So just like you can do with linear, you can pretty much do the same thing with rotation. You just have to take into account the rotational piece, which usually, if not always, comes from the radius. In the next video, we'll talk about conservation of angular momentum, and that's where we'll actually combine linear and rotational motion in the same problem. So that'll be a really important problem and a pretty fun one as well. So make sure you stick around for that. Leave your questions down below about angular momentum, and have a great day.